Okay, let me continue again once again on shallow foundation. And in the previous lecture, I have discussed about something on combined footing, and that is also one type of shallow foundation. And there are another type of combined strap footing is there, but I am not discussing that. Let me go to another type of strap footing, another type of shallow footing, shallow foundation in fact we can say, and that is actually raft or mat foundation. And I have the way I have mentioned that most of the time one column will be connected with the footing, that is called isolated footing, and when isolated footing is not suitable because of some reason, we are going for a combined footing, and where the different situation suitable for combined footing I have mentioned. Similarly, where exactly we require mat foundation, I will go for first and then different types of mat foundation I will discuss, and then I will close today the bearing capacity or shallow foundation topic with a summary. Let me see that like mat foundation need. Okay. Mat foundation is when the subsoil is weak and column loads are so heavy, the conventional spread footing cover more than 50% of the building area. So, now this suppose you have a number of columns, suppose like this, I just put a dot, suppose these are the location of columns, column, these are dots are actually column, and if I design suppose the foundation soil condition is not good, and if I try to design isolated footing all, then you will be covering almost entire area isolated footing. So, instead of doing so many small footing, it will be easier to give a common foundation here. Okay. So, that is the one of the areas where actually we go for mat foundation. That means, when the subsoil is weak and column loads are heavy, and because of that if you design the conventional spread footing, then it will be covering more than 50% or even 70-80%. In that situation, it will be better to have a common foundation, that is called mat or raft. And a mat is preferred to the individual footing when the soil mass is very erratic and contains pockets and lenses of compressible soil. That means, the foundation building area, suppose this one, and within this area there may be a large variation in soil type. So, in that case, if I do isolated footing, the different footing will behave differently, and then that create some problem to the building, and it will give distress to the building elements, that will column and beam, it will be some problem will be the cracks will form. So, that is another area when the below the cover area of the building, if the soil vary too much and there are lenses of compression of some soil, some corner suppose there is a compressible soil, some side may be good soil. In that case, if I use the isolated footing in different places within this zone, then it may have the problem to the building. That is another area where actually go for a common foundation, that is called mat and raft. And when actually because of this different condition, different loading and all those things, and if we design for individual footing, then what will happen, different footing also will settle differently. That means, differential settlement may be a problem. So, because of that if there is different columns having different loading and too much variation is there, and soil is also different, then there is a chance of having differential settlement, and that differential settlement there is a limit actually. If it goes beyond that, it creates problem to the building. So, that is another reason where actually if you go for this type of common foundation mat, that will give a bridge mat, that mat bridges over the patches of the weak soil, and the differential settlement is considerably reduced. Okay. So, because of this, instead of two different soil, two different footing, then they will settle differently, but if I give a common mat, then they will try to settle together and it will minimize the differential settlement between the two footings. So, these are the different areas where we can go for mat and raft foundation. And then now we will see the types of mat or raft in the next slide. You can see there are several types of raft or mat foundations are available. First one is here, that is flat plate. That means what? You can see I have shown here both the plane, this is the plane, these are the column location, these are all the black spot or column location, and this this outer boundary is the boundary of the foundation. And if I take a section here, then I will see this is the building part and this is the foundation part. That means what? The common plate like throughout the building, just like a thick plate first constructed, and through that plate the columns are erected. So, that is called flat plate type your mat foundation or raft foundation. Similarly, almost similar that it will be flat plate only, but in the column location, in the these are all column location, these are all different columns. In the column location, wherever there is a column, below the column there may be little thickened bottom side. Initially there will be some extra structural part will be there, and wherever there are columns, and just over that that means your this plate will be thickened at this column location. You can see here it is here and it is here like this, and then again over that flat plates are constructed and from there actually columns are erected. That is called flat plate thickened just below the column location only. And this is actually another type, actually beams and slab. That means what? You can see this, the slab will be there, but below the slab there will be beams. So, that means these columns will be connected by one beam, and this side also connected by beam. So, initially there will be beam like structure on the ground, and then when these two beams are meeting here, from this point the columns will be erected. From when it is meeting here, columns are erected. So, that means this will be designed as a beam, this will be designed at the beam with that different loading here and here, and then over that there will be a plate. So, below the plate there will be like a beams both direction. So, this direction beam will be connected by this beam, this direction columns will be connected by this beam. That there are like there is a net like structure will happen first, beam both direction, and on that beam we will have a flat slab, and then on that slab there will be from the all columns will be erected. So, this is called beams and slab type of mat. Next one you can see this is actually flat plates with pedestal. You can see initially there will be flat plate like a concrete mat will be constructed, and wherever there is a column. So, before starting the column there will be little wider a pedestal will be made, and from there it will be column will be little reduced to it, and then it will be erected. So, you can see this is actually column, the black one, and because of pedestal will be this is widened, and from the center of this the finally column will be erected. So, this is actually flat plates with pedestal. That means below the column, below the footing, like pedestal footing is to be there, like if I have footing can be two types. One is footing, one column is like this is one type of footing, and another type of footing is pedestal. That means this is coming like this, then pedestal will be there, and then you have actual footing. This is called pedestal type of footing. So, similar type of things will be here, every column location this pedestal will be there. So, this is called flat plates with pedestals. And then another type of is called slab with basement. That means, you can see this cross section, you can see this cross section here. This should supposed to be dotted actually, you will not see this supposed to be dotted actually, and this should be dark, the outer boundary. You can see that initially there will be plate at the bottom, and then there will be wall, basement wall, then again there is a plate, and in between there may be wall, because if the building width is suppose 20-30 meters, that slab cannot be so wide. So, in between there need support. So, in between along the column direction, you can see the column direction there will be wall, intermediate wall, and so that means the base, this is outer wall and this is intermediate wall. In the similar, this is actually in this direction. So, other direction also similarly will have wall. So, this is actually this part entire box type of structure with basement wall and basement bottom floor, basement top floor, this total together is as a foundation, and from this basement structure that columns will be erected for the building. So, that is actually slab and basement, and this basement area can be utilized. Many buildings will have basement floor, sometimes more than one will be there. So, this is also one type of mat foundation or wrapped foundation. So, these are actually just for the just to mention or to show what are the different types of foundation available for shallow foundation. I am just giving this one. The design of the mat foundation actually out of the scope of this course, because it is a totally concrete design actually. So, when there is a slab type, so you have to design as a slab. When it is a slab connected with beams, the first beam has to be designed, then slab has to be designed individually. So, there are some procedures. So, I will not go in detail. So, only this is also one type of shallow foundation, and I am just mentioning that. So, with this actually basically your shallow foundation topic is complete. Now, what I will do, whatever by 10 lectures actually whatever I have given, I will try to quickly summarize, so that it will be helpful to you to memorize what is which part is important and which you have to study with more detail. So, I will summarize very quickly. You can see that I have defined different types of pressure, that is ultimate bearing capacity in the form of, that means ultimate bearing capacity is what actually when there is a footing, if you continuously you load it, then sometime it will fail. So, before failure whatever pressure it is taking, that pressure actually ultimate pressure, and we denote by QU. And net ultimate means if the footing is placed at some depth, that because of this excavation work surcharge, so that should be deducted. So, net ultimate actually ultimate minus the surcharge, and net shape is what actually net ultimate divided by factor of safety. Ultimately, we use the pressure with some factor of safety. So, net shape actually what net ultimate divided by factor of safety, and here factor of safety generally between 2 to 3 for foundation engineering. And finally, what will be using shape bearing capacity or allowable bearing capacity, that will be equal to QNS, that means from this equation, and add gamma df surcharge finally, because gamma df itself no factor of safety is required. So, because of that I have applied factor of safety here, and finally, I am adding there. So, QNS will be QNS plus gamma df, that is QNU by Fs plus gamma df, this become actually finally allowable bearing capacity, and that has to be used for all calculation, sizing of footing, etc. Now, after defining this, I have described Terzaghi's bearing capacity, what are some assumptions, etc. that also you have to go through, but I am not going to those assumptions. Only thing, Terzaghi initially gave for C5 soil for steep footing ultimate bearing capacity in general shear failure condition, and that based on general shear failure steep footing bearing capacity was given by Terzaghi in terms of 3 factors NC, NQ, N gamma. They are CNC plus QNQ plus half gamma Bn gamma, and this NC, NQ, N gamma is a function of phi, and it is available in the form of chart table. And So, this is the one given by initially for C5 soil by strip footing, and if we then he has suggested also for, so ultimate bearing capacity for square footing he has given by this equation 1.3 CNC plus QNQ plus 4.4 B gamma N gamma, and similarly for circular footing he has given 1.3 CNC QNQ plus 0.3 B N gamma. You can see from the strip footing what is the difference, it is 1.3 multiplied here, and for strip footing it is 0.5, when it is circular square it is 0.4, when it is a circular it is 0.3, and B here actually when it is strip footing it is width of the footing, when it is a square footing it is a width again, and when it is a circular footing it is a diameter. So, these are the things to be remembered. Now, if this equation can be modified to different condition or this equation can be modified for different condition, that is what is the condition. If I consider for a cohesive soil, that means phi equal to 0, then if you go to the table you will see that Tarjagi's table NC is 5.7, NQ is 1 and N gamma is 0, and if I use those in the appropriate equation for cohesive soil phi equal to 0, and then you will see that, and then ultimate bearing capacity of footing resting on cohesive soil, that means this is the footing and the soil is this and this is cohesive. In that case actually surcharge part also not there, since C is 0, then since NQ is N gamma is 0, third part also will not be there. So, because of that Q ultimate bearing capacity of footing resting on cohesive soil will be only 5.7 C for strip footing, and this NC is 5.7, C is given by Tarjagi. So, 5.7 C for strip footing, and when you will go for square footing then it become 1.35 into 5.7 C. So, it will 7.41 C for square footing, and if you go for your it is of course both for square and circular, actually you can see if this is 0 and if this is not there, so only this is the value. So, both for square and circular footing the ultimate bearing capacity of footing resting on cohesive soil will be 7.41 C. So, these are the things, that means general equation is there, for a particular case I can modify to the equation this form. Next is actually suppose ultimate bearing capacity of footing embedded in cohesive soil. Now, I have taken previous one I have taken what? I have taken footing like this is the soil. Now, I am considering the ultimate capacity of the footing embedded. Okay. So, this is cohesive soil, same soil, but it is embedded now. So, for strip footing now, for strip footing it will be 5.7 C, it will be remain same, and now second part was Q and Q, since NQ is 1. So, if I add NQ 1 and add Q, so that means 5.7 C gamma dA for this will be the ultimate bearing capacity of a footing embedded in a cohesive soil is this. Similarly, if I go for square or circular footing, then what will happen? Gamma part still is missing. So, it will be Q will be 1.3 into 5.7 C plus gamma dF both for square and circular footing. It will be same until unless gamma part is there, there is no difference between strip and the square and circular footing. So, this is actually when it is embedded, when the footing is embedded, and when it is footing is surface, that I have shown 3 equations, 2 equations. When it is embedded, these 2 equations are applicable. Now, I will see that ultimate bearing capacity of footing resting on cohesionless soil, that means C is 0 and Q is 0, because if the footing now what footing I am considering? I am considering footing resting on sand. Sand means C equal to 0 and resting on ground means Q also equal to 0. that means first two part will be absent. So, if you take the first equation or Terzaghi's equation for strip, then your Q ultimate become half gamma B n gamma, and if you go to the circular square footing, then you will see 0.4 gamma B n gamma, and if you go for circular footing bearing capacity from Terzaghi's equation, you will see that it is 0.3 gamma B n gamma when it is on the surface. So, footing on the surface of a cohesionless soil. So, that is these are the equation. Next is effect of water table. See, these are the Terzaghi bearing capacity you have shown, and Terzaghi's bearing capacity while developing, what was the assumption? If the footing is here and this is the footing and it has a typical failure zone, and so this is the failure zone. So, water table will be much below that zone, and that depth actually generally required depth is B. If the water table beyond the B depth from the base of the footing, then whatever formula I have mentioned, those are applicable without effect of water table. Now, if the water tables vary from here to it goes up, then water table will that is actually bearing capacity will change, and that application of that also have shown in detail, but only for a particular case I will give an example where suppose ultimate bearing capacity of footing resting on cohesionless soil, suppose cohesionless soil and it is resting on cohesionless soil and water table is at great depth, then this will be the equation half gamma B n gamma. But now, water table suppose goes up and finally came to the base of the footing. In that case, what will happen? That gamma will be replaced by gamma submerged. You can see here that when water table at the base of the footing, that means on the ground surface, then your ultimate bearing capacity will be half gamma submerged B n gamma, or gamma submerged will be equal to gamma saturated minus gamma W. So, this is the effect of water table. Similarly, if the water table is changing from in between, then you have to take effective unit. If the water table is here, then in the surcharge also you have to take submerged unit weight, all those things I have shown. So, these are one example the effect showing the effect of water table. So, that has to be also carefully you have to study. Next part is Meharov theory. Then after Terzaghi's theory I have discussed also Meharov theories. While discussing Meharov theories, what I have discussed, I have introduced three more factors. What are those? One is actually shape factor, depth factor and inclination factor. Shape factor for all three, suppose SC, SQ, S gamma, and depth factor DC, DQ, D gamma, and inclination factor IC, IQ, I gamma. So, all those things also I have given, but this is a generalized equation. If there is no inclination, then I become 1. If there is a depth is not if the footing is at the surface, then depth factor also become 1. So, it will be modified. Again, if there is a cohesionless soil, C part will be 0. If it is a cohesive soil, then this part will be 0. So, this equation also similarly can be modified for the situation where it is, and in addition to that, because of the shape, depth and inclination, we can introduce different parameters, and those things I have given. And the way we have applied the effect of water table in Terzaghi's bearing capacity theory, all the effects similarly can be applied here wherever applicable. So, that I am not going in details, it will be similar. I hope that will be okay for you. I will not repeat that part. Next is Next is actually eccentric loading. When the footing is loaded eccentrically, then the use of effective width concept can be used. Suppose if the footing is here, this is the footing area, if the load is applied here, it is concentric and then it will have uniform pressure, but if it is a load is applied somewhere here, then it is eccentric. To make the uniform pressure, then what you have to do? You have to make this as center of the footing, and if you want to make this as center of the footing, then this some portion of the footing will become ineffective. So, you have to finally find out the effective width of the footing. How to find out? That B dash will be B minus 2 times eccentricity. Once you get this B dash, that same bearing capacity equation can be applied 1.3 cc, suppose it is square footing 1.3 cnc plus qnq. This is this part is not there, 0.4 this is not there, 0.4 B dash gamma B n n gamma. So, why B dash? B dash is modified width has to be used, that is the only difference you can do. And finally, to find out the ultimate load in the footing, what you have to do? Q multiplied by small q multiplied by the area of the footing is the ultimate load. Here actually area of the footing become L and effective width. Okay. And if this is a two-way eccentricities, then I could have done L effective multiplied by B effective. So, that is one way of taking care of eccentricity in footing while finding out the bearing capacity of the footing. So, this is also I have shown with an example. Next part is another way, actually, as I mentioned that when the footing is eccentrically loaded, then because of this moment or if the footing carries both moment and compressive load, then pressure will not be uniform throughout the area of the footing, and somewhere it will be more, somewhere it will be less, somewhere there may be chance of doing negative pressure also. So, there are general. So, because of that, if the pressure become more sometime, so what you have to do finally? There is a Q allowable for any soil, Q allowable, and if there is a Q max, if you find out, so your Q max should be less than Q allowable. So, that has to be make sure. So, because of that, sometimes you have to find out what is the Q maximum. When one way eccentricity is there, then actually your Q minimum, this is the equation, and Q maximum, this is the equation. Generalized equation actually Q will be equal to P over LB plus minus m y by I actually, and if I put that value of I and eccentricity in the moment and I all if I put, then it will be modified to these two equation Q minimum and Q maximum in terms of length and width of the footing. So, you can calculate this Q maximum, and you have to make sure that Q maximum should not be more than the Q allowable of the soil. Similarly, if there is a footing, if there is a footing and eccentricity two-way eccentricity, and this is x and this is y, and then there actually some of the foot load is acting here, then I can imagine load is acting here. Because of this loading there will be compressive, because of the P, and because of the moment, because of this force, because of moment with respect to this side, here it will be compressive, here it will be negative. Similarly, because of the loading here, because of the moment with respect to this axis, moment with respect to positive here and negative here. So, that means this point actually, because of the load that will be compressive, because of the moment with respect to this axis positive, because of the moment with respect to this axis that will be positive. So, that means all three will become positive, it become heavily pressurized. This point pressure will be maximum, and whereas here because of compressive positive and because of this moment with respect to this axis negative, moment with respect to this axis again negative, that means it become very less. So, what is the minimum and what is the maximum here, that also can be obtained, and this is the equation given. Q minimum is this and Q maximum is this. A generalized equation actually Q will be equal to P over area plus minus, suppose m y, suppose this is moment with respect to the m y multiplied by x divided by I y plus minus m x with respect to this moment m x multiplied by y divided by I x. This is the generalized equation, and if I put the I x, I y and y value and moment in terms of P and E, then that equation will be modified to this and this for maximum and minimum. And finally, after finding out the maximum value and minimum value, you have to compare with the allowable value, and you have to make sure that this maximum value is not greater than the Q allowable. So, that is the check has to be done when the eccentric. So, these are the things I have covered, and towards end also I have covered other type of combined footing etcetera, which I have just done. So, because of that I have not summarized this one. Otherwise, with this the shallow foundation, bearing capacity and some sort of design aspect is complete, and I will stop here. The bearing capacity, I will go for next topic in the subsequent week. Thank you.